Have you ever looked up at the night sky and wondered how the stars move? The vast expanse above us is a constant reminder of the mysteries of motion. Or perhaps you've marveled at the speed of a cheetah chasing its prey. The sheer agility and speed of this magnificent creature are a testament to the principles of motion. These questions and countless others about the world around us fall under the domain of mechanics. Mechanics helps us understand the fundamental principles that govern the movement of objects. Mechanics is the branch of physics that delves into the fascinating world of motion. It provides the tools and frameworks to analyze and predict how objects behave when forces are applied. It seeks to answer fundamental questions about why and how objects move the way they do. From the swing of a pendulum to the orbit of planets, mechanics is everywhere. Mechanics is broadly divided into two main branches, kinematics and dynamics. Each branch offers a unique perspective on the study of motion. Kinematics is like the descriptive storyteller. It paints a picture of motion, detailing the paths objects take and the speeds at which they travel. It describes the motion of objects without delving into the causes. Imagine watching a ball roll down a hill. Kinematics tells us how fast and how far it goes. Imagine watching a car zoom past you. The speed and direction of the car are all part of the kinematic story. Kinematics helps us answer questions like, how fast is it going, or how far did it travel? It provides the quantitative details of motion. It's all about quantifying motion using concepts like speed, velocity, and acceleration. These measurements are crucial for understanding the dynamics of any moving object. Dynamics, on the other hand, is the detective of the story. It seeks to uncover the reasons behind the motion. It digs deeper into the why of motion. Why does an object start moving, stop, or change direction? Why is the car moving? What initiates its motion and what keeps it going? What caused it to accelerate or decelerate? These are the questions dynamics seeks to answer. Dynamics introduces us to the concept of forces, the unseen agents that govern motion. Forces like gravity, friction, and tension play crucial roles in the movement of objects. It's like solving a puzzle where forces are the missing pieces that complete the picture. Understanding these forces allows us to predict and control motion. Together, kinematics and dynamics provide a comprehensive understanding of motion. They are the twin pillars of mechanics. They form the foundation of classical physics and have far-reaching applications in various fields, from engineering and architecture to robotics and space exploration. The principles of mechanics are integral to the design and function of countless technologies. In the vast expanse of the cosmos, everything is in a constant state of motion. The laws of mechanics apply universally, from the smallest particles to the largest celestial bodies. From the smallest subatomic particles to the largest galaxies, nothing stands still. Every entity in the universe is governed by the principles of mechanics. Understanding the principles of mechanics allows us to unravel the mysteries of this cosmic dance and appreciate the intricate workings of the universe. It is through mechanics that we gain insight into the fundamental nature of reality. Imagine a leaf falling from a tree. It gently floats down, carried by the wind, its path a graceful dance through the air, twisting and turning as it descends. Now picture a car speeding down a highway, its engine roaring as it devours the miles, a blur of motion and power. Both the leaf and the car are in motion, but their movements are vastly different, each telling its own story. To understand these differences, we need to delve into the language of motion, a fundamental concept in physics. Motion, in its simplest form, is a change in an object's position over time. When we say an object is at rest, it means its position remains constant relative to a reference point, like a marker in space. For instance, a book lying on a table is at rest relative to the table, unmoving and steady. However, relative to the sun, the book, along with the Earth, is hurtling through space at an incredible speed, part of a cosmic dance. Motion comes in various flavors, each with its own unique characteristics. Uniform motion, as the name suggests, is characterized by constant speed and direction, unchanging and predictable. Think of a train cruising at a steady pace on a straight track, a perfect example of uniform motion. Non-uniform motion, on the other hand, involves changes in speed, direction, or both, making it more complex and dynamic. A car navigating a winding road is a perfect example, constantly adjusting its speed and direction. Motion can be further classified based on the path an object takes, adding another layer of understanding. Rectilinear motion describes movement in a straight line, like a ball rolling down an inclined plane, simple and direct. Circular motion, as you might have guessed, involves movement along a circular path, like a satellite orbiting the Earth, bound by gravity. Periodic motion, a special type of motion, repeats itself after a fixed interval of time, like the swinging pendulum of a clock, rhythmic and predictable. Understanding these different types of motion allows us to describe and analyze the movement of objects around us, from the smallest particles to the largest celestial bodies. It's the first step in our journey to unravel the secrets of motion and unlock the mysteries of the universe, a quest that has fascinated humans for centuries. In the 17th century, Sir Isaac Newton, an English physicist and mathematician, revolutionized our understanding of motion with his 3 laws of motion. These laws were groundbreaking and have stood the test of time, forming the foundation of classical mechanics. These laws, etched in the annals of science, are the bedrock of classical mechanics, providing a framework to explain the motion of objects from apples falling from trees to planets orbiting stars. They help us understand the natural world and predict the behavior of physical systems. Newton's first law of motion, often called the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This principle explains why a vehicle continues to move forward even when the engine is turned off, until friction or another force slows it down. Imagine pushing a shopping cart. Initially, it takes some effort to get it moving, but once it's in motion, it's easier to keep it going. This everyday experience is a perfect illustration of inertia. This is inertia at play, the cart's tendency to resist changes in its state of motion. The same principle applies to all objects, whether they are at rest or in motion. Newton's second law of motion delves into the relationship between force, mass, and acceleration. It provides a quantitative description of the changes that a force can produce in the motion of an object. It states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. This means that heavier objects require more force to accelerate than lighter ones. In simpler terms, pushing a heavier shopping cart requires more force to achieve the same acceleration as a lighter one. This principle is crucial in understanding how different forces affect the motion of objects. Newton's third law of motion, often paraphrased as "for every action, there is an equal and opposite reaction," elucidates the nature of forces. It explains how forces always come in pairs. When you jump on a trampoline, you exert a downward force on it. This action force is met with an equal and opposite reaction force from the trampoline. Simultaneously, the trampoline exerts an equal and opposite upward force on you, propelling you into the air. This interaction of forces is a fundamental aspect of motion. Newton's laws of motion are not just abstract concepts confined to textbooks. They are woven into the very fabric of our daily lives. They help us understand and predict the behavior of objects in motion. From the simple act of walking to the complex maneuvers of airplanes, these laws govern every motion we witness and experience. They are the guardians of motion, ensuring that the universe operates in a predictable and orderly manner. Imagine trying to walk on a perfectly smooth surface like ice. Your feet would slip and slide, making it nearly impossible to move forward. This is where friction, a force that often goes unnoticed but plays a crucial role in our daily lives, comes into play. Friction is the force that opposes motion between two surfaces in contact. Friction arises from the irregularities present on even seemingly smooth surfaces. When these irregularities interlock, they create resistance to motion. The amount of friction depends on factors like the nature of the surfaces in contact and the force pressing them together. Rough surfaces like sandpaper generate more friction than smooth surfaces like glass. Friction, while often seen as a hindrance, is essential for many everyday activities. It allows us to walk, drive cars, and even hold objects in our hands. Without friction, life as we know it would be impossible. Imagine trying to write with a pen on a frictionless surface. The pen would simply slide without leaving a mark. Friction manifests itself in various forms. Static friction prevents objects from moving when at rest. It's the force you need to overcome to start pushing a heavy box across the floor. Kinetic friction acts on moving objects, slowing them down. It's the reason a ball rolling on the ground eventually comes to a stop. Rolling friction, as the name suggests, comes into play when an object rolls over a surface.